Welcome to Chapter 2, which covers modeling distributions of data. So we've already looked at a little bit of modeling. We're going to be focusing on numeric data in this section, and we're going to be looking at numeric measures of these numeric data. So far with numeric data, we've looked at mean, median, IQR, standard deviation, things like that. But we're going to continue with that by looking at some specific types of distributions, some ones that are really common and more measures that we can calculate. So in this first video, we are going to describe location in just a given numeric distribution. We are going to talk about percentiles. We are going to talk about cumulative relative frequency graphs. We're going to talk about z-scores. And then the last bullet point there has to do with transforming data. So if you don't have a calculator, you're going to need a calculator. There's more numeric measures this section, and then of course we're going to keep interpreting. So let's get started. Percentiles. You all have probably heard percentiles before with test scores, in particular standardized test scores. So when you took your SAT, you might have found that you were at the 80th percentile in math maybe, or the 43rd percentile in reading, let's say. A percentile describes location in a distribution. Specifically, a percentile tells us the percent of data at or below that value. Now, there are already 3 percentiles that you all know. We know the median. The median is the 50th percentile, and that should make sense. 50% of the data falls at the median or below it. We know Q1, the lower quartile, that's the 25th percentile. 25% of the data falls at that value or below it. And then the last one that we already know is Q3 is the 75th percentile. It is very important to know that percentile does not indicate percent correct. So if on the SAT you scored at the 70th percentile in reading, that does not mean that you answered 70% of the questions correctly. That means you did the same or better than 70% of the test takers. So only 30% of people did better than you in that section. So let's take a look at an example using percentiles. The stem plot below shows the number of wins for each of the 30 Major League Baseball teams in a recent season. Okay, so we have our stem and leaf plot, and we have our key, which tells us that 5-9 is 59 wins. We are going to calculate and interpret the percentiles for the Colorado Rockies, the New York Yankees, and the Cleveland Indians. If we start with the Colorado Rockies, who had 92 wins, that's this team right here. So we want to know the percent of teams that were at or below 92. So one thing that we could do is calculate that, right? Count it. So we have that 92. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So 25 of the teams were at or below those 92 wins. If we divide by the total of 30 teams, we get about 0.833, and so on and so forth. So we would say that the Colorado Rockies are at the 83rd percentile. So that is our first answer. That at is very important. A lot of people want to say something like the Rockies are in the 83rd percentile. That's not true. A percentile is a boundary. It's a boundary. It's not an interval. So our Colorado Rockies are at the 83rd percentile. Now, if we look at the New York Yankees, we're just going to skip that New York Yankees one. We don't need to do 3 of them. We're going to go on to the Cleveland Indians, though, that had 65 wins. So the difference here is we notice that there are 2 65s. Pick either one. Pick either one. Doesn't really matter. I'm going to choose that second one. So we have then 1, 2, 3, 4, 5. So if we take 5 out of 30, we can say that the Cleveland Indians are at about the 17th percentile. On a multiple choice question, I would not give you options of 5 out of 30 or 4 out of 30. Either one will be acceptable. So that is the start of percentiles. Where we go from here is it leads us to something called a cumulative relative frequency graph. And so that's what you see on the right. And if we notice some of our labels, label on the x-axis is points scored per game. And as it says in the description, we're looking at 486 NBA players. And then we have cumulative relative frequency on the graph. So cumulative relative frequency tells us the relative frequency at that point and below it. So this point, for example, tells us that 10 points, at 10 points, the cumulative relative frequency is about 0.7. So 70% of the players scored 10 points or below it. Similar idea here, about, let's say, 32% of the players scored 5 points or below per game. Keeping that interpretation in mind, let's look at the first part, which is part A. One of the players scored 12.4 points per game. What percentile is he at? Okay, so logically, the first thing we're going to do is locate 12.4 on the graph. Even if you don't understand what the graph means, we should know you're going to need it. Okay, 12.4, right, as an average of points scored per game is about there. So then if we go up, this is our point. So it looks like that is about at 12.4, 0.77. So what that would tell us is that 77% of players scored 12.4 points per game or less. Now, that was just extra information that didn't actually answer the question. The question is, what percentile is he at? This player is at the 77th percentile. Okay, so then next question, what is the 25th percentile? 25th percentile, 25% of the data falls at or below that value. So if we look on our graph at 0.25 and go over, it looks like the 25th percentile is about 4 points per game. And what is another name for this value? This is the lower quartile, like we talked about above. Okay, so then last, part C, we are making a relative frequency histogram of these data. Okay, so let's start with what is this going to look like? So of course we're going to have a title. On our x-axis, we're going to have points scored per game. The difference here is that relative frequency needs to be on the y-axis, not cumulative relative frequency. Okay, so then I'm going to put my same scale as has above, 0 to 35. Okay, so 0, 0 is going to stay the same. If we look at that 0, 5, between 0 and 5, that's about, 30% of the data. So it's going to start out the same way. And then I'm going to tell you how that changes. So from 0 to 5 is about, 32% of the data, about 0.32. Okay, so now if we go to 10, so if we go to this point right here, that looks like it's 10, let's say about 0.7. Now, that does not mean that the relative frequency is 0.7. What that means is from 0 to 10 is 70% of the data. 0 to 10 is 0.7. But we already know that between 0 and 5, we've got a point about 0.32. So here's about 0.32 of the data. If I'm totaling up to 0.7, then that means right here, I'm going to have about 0.38 so that I can get up to that 0.7. So between 5 and 10 is about 0.38. Okay, so then likewise, if I go from 10 to 15, this point right here looks like it's about 15, 0.88. Okay, so I'm going to switch to a highlighter. We know between 0 and 10 is 70% of the data. Then we know between 0 and 15 is 88% of the data. So to get from 70, so 0.7 to 0.88, I had to move about 0.18. And then you're going to keep going. It's a similar idea from there. So you end up with something that looks like this, and it continues. Okay, so again, I know that's a little confusing. You might need to go back and re-listen to that part. But to get that 15 to 20 part, you're looking at up until 15 is 88% of the data. Up to 20 is about 92% of the data. So that means this bar is about 0.04. And then, of course, we would put a title here. Now, these are two different graphs, obviously, that give us different information. And so some things that I might ask you is I could ask you in the cumulative relative frequency graph, I might ask you, where is the graph the steepest? And what does that tell us? So the fact that the graph is really steep here, what does that mean? I might ask you, where is the graph the flattest? What does that mean? So this graph is really flat here. What does that mean? Well, hopefully we can tell that means not very many players scored between 25 and 30 points per game. If the graph is steep, like where we said before, here between 5 and 10, a lot of players scored between 5 and 10 points per game. Okay, so that was really kind of the first objective that we had, which was percentiles. First and second, because the second one was cumulative relative frequency. So next thing that we're going to do is we're going to compare observations. So please look at the next page. Macy, a 3-year-old female, is 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy, but who is taller, relatively speaking? So what I mean by that, if we compared Macy to other 3-year-old females or Brody to other 12-year-old males, who would be taller? So that is relative to other kids of the same ages, who is taller. According to the Centers for Disease Control and Prevention, the heights of 3-year-old females have a mean of 94.5 and a standard deviation of 4. The mean height for 12-year-old males is 149 with a standard deviation of 9. Okay, so here's what we got. We have Macy. She is 100 centimeters tall. Comparatively, girls her age have a mean of 94.5 centimeters and a standard deviation of 4 centimeters. Brody, on the other hand, is 158 centimeters. Compared to males his age, the mean is 149 centimeters, and the standard deviation is 9 centimeters. Okay, so without really knowing the stats behind this, let's look at a little bit of reasoning. We notice that Macy is about 5.5 centimeters taller than the average for her age. Brody is about 9 centimeters taller than the average for his age. And so the question is that a big difference? Is 5.5 centimeters a big difference? Is 9 centimeters a big difference? The way to answer that is we're looking at the standard deviation. Macy is more than 1 standard deviation above what's expected for 3-year-old females. Brody, on the other hand, is only 1 standard deviation taller than males for his age. So saying that again, Macy is more than 1 standard deviation taller than we would expect her to be. Brody, on the other hand, is only 1 standard deviation taller than what we would expect for his age. So Macy is taller. Now, what we just reasoned out is we calculated in our heads what's called a z-score. So the way to calculate a z-score is we take an observation, we subtract the mean, and we divide by the standard deviation. Okay, so for Macy, we take her 100, and we subtract that 94.5, and we divide by 4, which gives us 1.375. And what we did in our head is we came up with that number. That is the number of standard deviations she is above the mean. And then we did the same for Brody. We calculated the difference between his height and the average. We said that was 9. Dividing by the standard deviation gave us 1. So again, what that told us is that Brody is 1 standard deviation taller than the average for his age. Whereas Macy is almost 4 standard deviations taller than what we would expect for her age, hence why she's taller. So z-scores are a way for us to compare two different values from different distributions. Maybe we want to compare salaries. I got my salary as a first-year teacher. I have a friend who got a salary as an actuary. She was making more money than me because she was an actuary, but how are we doing in our own career fields? Way to answer that is to look at a z-score. Okay, so going on to z-scores. Do z-scores have units? No. No, z-scores are considered standardized. Standardized, it's a way to get rid of the units so that we can compare. What does the sign of the standard deviation tell you? Well, in our case, we had positive z-scores, which means we are above the mean. So positive is going to be above the mean. A negative z-score is below the mean. Now, you got to think really carefully here. You don't always want a positive z-score. That's a lot of times what people think, but you got to think about the context. If I'm looking at taking a test, for example, I want a positive z-score. I want to do better than the average. But if I'm a runner, I don't want a positive z-score. If I'm a runner, a positive z-score means that I am above the average. I'm slower than the average time. So in the case of running, you might want a negative z-score. You want to be below or faster than the average time. Okay, so we are going to look at a few more examples. Moving on. The single-season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 1961, Mark McGwire hit 70 in 1998, and Barry Bonds hit 73 in 2001. In absolute sense, Barry Bonds had the best performance of these 4 players because he hit the most home runs in a single season. However, in a relative sense, this may not be true. Baseball historians suggest that hitting a home run has been easier in some eras than others. This is due to many factors, including quality of batters, quality of pitchers, hardness of the baseball, dimensions of ballparks, and possible use of performance-enhancing drugs. To make a fair comparison, we should see how these performances rate relative to other hitters during the same year. Calculate the standardized score for each player and compare. Okay, so if we look, Babe Ruth hit 60 home runs. What this table is telling us is that the average for players in 1927 was 7.2 home runs, and the standard deviation was 9.7. Now, what you're going to notice is when we get to Barry Bonds, who had the highest, the mean also increased. So it was more likely that people were hitting home runs, and the standard deviation is higher as well. So it's not so easy just to look at Barry Bonds and say, well, Barry Bonds hit the most home runs, and so he was the best player. That's not necessarily the case. Because the means change for each of the years, and so do the standard deviations, really the most fair way to compare is to calculate a z-score. So that's what we're going to do. I'm going to do Babe Ruth first. So I'm going to take his home runs, subtract the mean, and divide by the standard deviation. So for Babe Ruth, that gives a z-score of about 5.44. So Babe Ruth scored about 5.44 standard deviations more than the mean in 1927. Okay, hopefully you get the idea. If you want to take a minute or two to pause the video and do the other 3 players, you can. If not, I calculated them and I will tell you what I got. So for the other players, for Roger Maris, I got a z-score of about 3.15. For Mark McGwire, I got a z-score of about 3.88. And for Barry Bonds, I got a z-score of about 3.91. Okay, so Babe Ruth had the highest z-score. So while his home run average wasn't the highest, what this tells us is that Babe Ruth hit the most home runs in comparison to the other players in 1927. So while Barry Bonds has the record for 73, Babe Ruth's record really was the most impressive or the most unusual. Okay, in 2001, Arizona Diamondback Mark Grace's home run total had a standardized z-score of negative 0.48. Interpret this value and calculate the number of home runs he hit. First thing, negative means below the mean. So if we're interpreting Mark Grace or Mark Grace's home run total was 0.48 standard deviations below the mean for players in 2001. So using our z-score formula, if we take that negative 0.48, that would be equal to his home runs, subtract the mean in 2001, which is 21.4, divided by standard deviation. And this is what we're calculating. So that is what you're going to have to solve. If we put this over 1 and cross multiply, we would end up with x subtract 21.4 is equal to negative 6.336. So then if we add 21.4, it looks like Mark Grace's home run total was about 15 home runs. And we already said it was below the mean, so we should end up with a number less than the mean of 21.4. Okay, before we move on to the last two objectives, here is some more computer output for you to see. Some things I could ask you. This point in red, you might be asked, what is the percentile for that point? You could be asked, what is the z-score for that point? Right, and z-score, we have the mean, we have the standard deviation. You could be asked to describe the dot plot. You could be asked to make a box plot for it. So this is just some more computer output, similar to some that we've seen before, that you could be asked various pieces for. Okay, so let's move on. This is really an investigation that we were supposed to do in class, but since we're not together, we are just going to do it now, and I'm going to go through it with you. We're going to make a dot plot of the data and then calculate the following statistics. So here is our data right here. So we have 3 dots at 0. We have a dot at 1, a dot at 2, a dot at 3. And I'm just going to tell you the mean ends up being 1, the median is 0.5, the standard deviation is 1.3, and the IQR is 2. So now what we're going to do is we're going to add 5 to each value. So we have 0, 0, 0, 1, 2, 3. So if we add 5, we get 5, 5, 5, 6, 7, 8. So if we graph those, 5, 5, 5, 6, 7, 8. The mean now becomes 6. The median becomes 5.5. Take a little mental check. Do you think the spread changed? If you look, all we did was take the blue graph and shift it. Right? Shift it. So the center should change, but the standard deviation shouldn't, and it didn't. Standard deviation is 1.3. IQR is still 2. Okay, so where is that leading us? What is the effect of adding or subtracting a constant from each observation? The shape stays the same, no change. Right? We went from blue to red. It shifted, but the shape didn't change. The spread also didn't change. The center, though, did. When we added 5 to each observation, it did the same thing with the mean and the median. So the center, we are going to add or subtract that same constant. So this right here is key. This is key. What we did up here in 1 and 2 was just to demonstrate where this information comes from. This you are expected to know. We are not going to be graphing every time. Now we're going to talk about what happens if we multiply by a constant. So this time we're going to take those same numbers and we're going to double them. So we had 0, 0, 0, 1, 2, 3. So if we double them, we're going to get 0, 0, 0, 2, 4, 6. So if we graph those, 0, 0, 0, 2, 4, 6. Okay, so now calculating those same numbers. The mean is 2. The median is 1. Standard deviation is 2.6, and the IQR is 4. Now, it should not be a shock that the spread changed when we look at the graph, right? The graph got wider. It got less consistent. So what that's leading us to, again, is what happens if we are multiplying or dividing by a constant. Okay, well, the shape is still the same, right? It's more spread out, but our initial distribution was skewed right. This shape is still skewed right. Okay, the center, we would multiply or divide by that constant. Same thing with the spread. We would multiply or divide by the constant. And we can see that up here with the standard deviation and the IQR. Okay, one thing to note. This is the only thing that can be a little bit tricky. If we multiply by 2, like we did above, the standard deviation and the IQR are doubled. Variance, though, is different. Remember that variance has units that are squared. So the variance would actually be multiplied by 4 because that's 2 squared. So that's the only thing that's a little bit tricky is variance is a measure of spread, so it will be changed, but it would be multiplied by 4 instead of 2. Okay, so let's take a look at an example of how you might see this. In 2010, taxi cabs in New York charged an initial fee of $2.50 plus $2 per mile. The distribution of distance for one businessman was skewed to the right, with a mean of 4.8 and a standard deviation of 2.3. What are the mean and standard deviation of the costs of his cab rides in dollars? Okay, students tend to get these problems wrong because they don't show work. They just jump in and they start doing calculations. What I would suggest to you is that you start by taking all this information you have and writing it down. So first thing is we're talking about distance. So we know that for this businessman's distance, there is a mean of 4.8 miles and a standard deviation of 2.3 miles. What we want is we want the mean and standard deviation of the costs. That's what we're asked for. And so what we need to do before we start calculating anything is figure out what is the relationship between distance and cost. Okay, and so that's what that first sentence tells us, is that it tells us for the cost, there's $2.50 just for getting into the cab, and then there's going to be $2 charged per mile. Okay, so this is all the background. Write down what information do you have and write yourself a formula. What I have in red is what most people forget to write down. Okay, so if we want the mean and standard deviation, what we should be asking ourselves is the mean of the cost. If I multiply every observation by 2, does it change the average? Yes, of course it does. If I add $2.50 to every observation, does that change the average? Yes, it does. So if I want the mean of the cost, I'm going to take the mean of 4.8 and I'm going to multiply it by 2, and then I'm going to add that $2.50, which gives me a mean of about 12.1 or $12.10. So on average, this businessman spent about $12.10 on average for the rides. Now again, here's where people get tripped up. Standard deviation. Ask yourself the same thing. If we add 250 to every observation, does it change the spread? No. If we take our dot plot and we add 250 to every number, all it does is shift the distribution. It doesn't actually change the spread. So that 250 is not going to change our standard deviation. But the $2 will. So for our standard deviation, we're going to take that 2.3 and multiply it by 2. So our standard deviation is $4.60. Okay, so I wouldn't memorize what we did above, that 3 and that 5. Just think about, if I take a distribution and I add a constant, does it change the spread? No, all it does is shift it. If I multiply by a constant, does it change the spread? Yes. Okay, last question on this page before moving on. If he standardized each distance, what would be the shape, mean, and standard deviation? So if he standardized, what that means by standardizing each distance is changing it to a z-score. So if for every single ride, he took every ride over the year 2010 and he changed each ride to a z-score, the shape, going to be the same. So it said skewed to the right, the shape is still going to be skewed right. But here's the key, mean and standard deviation of z-scores. The mean of z-scores for a data set is always going to be 0. The standard deviation for z-scores is always going to be 1. So if you ever take a data set and change everything into a z-score, the mean will always be 0, the standard deviation will always be 1. Okay, we got a few more things to talk about, and then we will be done. So let's look at the next page. The distribution of the amount of time it takes Chris to get to work on the bus, including waiting for the bus to arrive, is shown in the dot plot. On about what percent of days does it take between 8 and 11 minutes? So first thing, if we're looking at this dot plot, talking about shape, maybe you remember this term, maybe you don't. This is a uniform distribution. If we draw a curve on it, it's about the same all the way across. And it looks like it takes Chris anywhere between 5 and 13 minutes to get to work on the bus. And all those times are about equally likely. So if we're looking for the percent of days it takes him between 8 and 11, we are looking 8 to 11. We are looking for this area. Now, we're not by any stretch going to count up all of those dots. What we're going to say instead is between 8 and 11 is 3, but then the total of the distribution from 5 to 13 is 8 wide. So if we divide that, we get 0.375. But answering the question on what percent of days, on about 37.5% of days, it's going to take him between 8 and 11 minutes. So what we have above, what we drew in blue, is called a density curve. So a density curve traces a dot plot or a histogram. So our blue uniform distribution that we drew in wasn't perfect, but it generally contained all of those points. Now, why did we use that? Why did we bother to draw that in? Well, if we really wanted to know what percent of days it took him between 8 and 11 minutes, we would have to count up all those dots. And I'm going to be honest, I don't want to do that. Hope you don't. I'm assuming you don't want to either. So why did we use one? So that we can avoid counting dots. Okay, and what you need to know, area under a curve, the area is always going to equal 1. Area under the curve is always going to be 1. And that's because this curve, we'll learn later, represents probability. Probability. So the entire curve, the entire probability is going to be 1. Okay, identifying mean and median. We've talked about this a little bit already. The median is the middle. Like in our case, the middle dot. So you're going to have to do a little bit of estimating where you think that middle dot is. The mean, like we talked about, is the balancing point. So if you think about each of those dots as a 1 point 1 pound weight, where would you be able to balance all of those weights? In our case, because that distribution above is symmetric, the mean and the median should be about equal. So that is a density curve. Next set of notes, we're going to look at one very, very specific density curve, which is called a normal distribution. This example below, we are not going to do. So this is the end of your notes for section 1. Thank you all for sticking with me. Please write down if you have any questions so that we can make sure to get those answered next time I see you. Thank you.